everybody. So, got a couple things to go over tonight. Well, the regular stuff for the module, the content, half of what's on the list for the to-do list to cover this week. To talk about it in lecture would be to write down the same list that's in the textbook. Actually, a little bit shorter on than the textbook. So, not gonna read the list, but I want to talk about arrays and tuples. I'll mention briefly strings very quickly, so we'll probably talk about spend about 15 minutes on that, maybe 20 minutes on that. And then something that I always want to cover in all my classes, and I think it's very, very important, and it was never covered in a single programming class I took. Never mentioned in a textbook on programming, never covered in tutorials. I took a lot of programming classes and it was never mentioned in any of them. And well, what we've been doing in here, right? We've been programming in Python. So we write a Python script, run it, test it. But have you ever gone to install a piece of software and received a Python script? Spider was written in Python, but did they give you a Python script when you went to install that? That's writing that script is not the end. There's another step of what we do when we're finished with the program. It runs when we're finished testing and debugging it. Refactoring it so that it looks all clean and organized and looks nice. That's what refactoring is. Don't overthink the refactoring assignment. Refactoring means clean up the code. I've always said, imagine you're never going to meet the person that maintains your code. The person that writes updates further down the line. 2 years from now, that software is going to be updated. And somebody else is going to handle the bug reports between now and then afterwards. Imagine that you're never going to meet that person and be as nice as you can to them. That's what refactoring is. Make sure everything's clearly labeled, if comments are needed, and make sure they can look at that code and know exactly what's going on, even if they never meet you. That's what refactoring is, so don't overthink it. Once your program works, just make it clean, organized, make it look really, really nice, as good as you can. I guess where that refactoring assignment showed up, it was kind of try to put it into functions. But I think I mentioned, I meant to copy and paste from a previous version of time I taught this course, because there's another one that instead of saying the sales tax program explicitly, I said choose any of your earlier programs. So any program that you've already written for the class refactor, it does not have to be that sales tax one. Because there are probably some other ones that would refactor a whole lot easier. But refactoring is just be as nice as you can to the person that's going to update you and maintain your code. That's what I've always said. And then there's a really good little comic strip came out a couple years ago about it. Let me see if I can find this. I'm not going to look for long. Comic about refactoring cycle. But lots and lots of jokes about refactoring. I don't see the one I was looking for. The comic I was looking for has a guy sitting there at his computer, obviously typing code or something, when somebody in a hockey mask and wielding a chainsaw kicks in his door, and like the scraping symbols for comic and all that. And the caption says, refactor your code like the person who comes back after you is a psychotic maniac that knows where you live. That's what refactoring is. Just make it clean, organized, be as nice as you can to the next person that's going to look at that. Clean it up, maintain it, make it look nice. Spread things out so it's easy to read. We haven't talked about patterns yet, have we? I'll talk about patterns soon. Sometimes it can be beneficial to zoom way out where we can't actually read the code and look at the patterns that code makes on the screen and track down bugs that way. Even if you just be staring at the code, reading word after word after word after word, you can't find it. You zoom way out and you'll suddenly see where the code pattern breaks, where it's not written the same way all of a sudden. It's like, oh, there's the problem. There's lots of little tricks we have to apply. Real quick about strings though. So to stand up here and lecture about strings, I would basically write down the same list of things that's in the textbook. So I'm going to use that as a point to express the point that I said earlier. Textbooks and tutorials, those are always introduction, starting out. They will never give you the full picture. So what you want to do is use that to learn to read the user manual. Because we do have an official Python user manual that tells you every single thing there is to know about Python, right? If we come over here and go to PyDocs, strings, PyDocs, it should go right to it, yeah. docs.python.org. So here's the user manual about strings. Every single possible thing that's there, not just that introduction that textbooks and tutorials will give you. But these are usually written by the people that wrote the programming language or the programming library, the module package, whatever we call it in the particular case we're in. In Python, we usually call it a module. And those people are really, really, really good at writing computer code. And quite often, they're not very good at writing English. So it takes some getting used to in order to read their English documentation. Or sometimes it might not have even been written in English. If you go hit the translate button on your browser and look through different languages, you might suddenly find it makes perfect sense in French. Just throwing a random one out there, I don't speak French at all, and it would still look like gibberish to me, but the automatic translator ended up being bad. But it would be consistent. So use your textbook and tutorials and that starting out reference material to learn to read this. Like look at that stuff, or look here first. It's probably not going to make much sense. Basically, strings have lots of methods built in. A string is not primitive data. A string is not a number. A character is primitive data. The letter A, letter R, the letter T, those are primitive data. And when we put them together, we get the word art. That word as itself is a combination of primitive data, which is an object. That's what we're going to talk about next week. So when we have combinations of primitive data, everything we need, all the methods, the behaviors, that combination of primitive data can carry out is included in it. And your textbook has a list, a good starting point. There's some you're going to use a lot. Right? Digits will pull. If you just want the string of all the digits, you can just type string.digits and it'll give you 0 through 9. There might be a use for that. It would probably take me a long time to think of a use. Like it doesn't choose one of them. We could index them. We could say string digits index 3, our 4th digit's going to return 3. But why would we do that when we can just type the 3? But they created that. It exists. So there's way more here than the book would cover. Format, we've seen that a few times. Deformat, I don't think that one's shown up yet this class, but we have more than one way to form. Right at the top, there's more than one formatter. Parse, that means read through a string and look for something. So it probably should have shown up when we were talking about text files. I guess last week's text files. We read the one from Monday night. We read through that text file and pulled out somebody's name and their rate of pay. We parsed that text file for the data we want. So that means read through a string and look for what we're wanting. Somewhere down here is a bunch of syntax. Y'all can look through that, and yeah, the lecture on strings would be standing up here rattling off the same list you can look at. And to start with, you probably want to use that list in your textbook because that was specifically designed as a good list for people starting into Python learning. But make sure you look at PyDocs and see what's there, and you're comfortable reading that because that has the full picture. And textbooks and tutorials will never have that full picture. But basically, it's a bunch of things. The behaviors we want from a combination of characters is already built in. Yep. Excuse me. That's taking a long time. I'm just going to jump over to the console terminal. That's quicker. So we have a string. What? Oh, we don't need to restore it. Probably deleted something. Have this string, just our standard word, and Python wants to spit that back out, right? But when we have a string, of that same string, can I just push it up? Yeah. We can do things with it. It's like, I wanted that all in uppercase. I think we saw this one earlier, dot upper and dot to lower with parentheses because it's a method. We want to do something. And we can just make that all uppercase or all lowercase. Or let's replace the letter L with a pound sign or hash key or whatever you want to call that symbol. We have a bunch of behaviors that are ready to go. And the way I was typing it was just because your textbook and tutorials probably never show that. We can do that. I didn't even save it. I just put the string and then just immediately went into the method. We would probably pretty much always do something like my string equals hello world. And then do all of that stuff, right? Then we say my string dot upper or my string dot lower and change it that way. What's going to happen when I hit enter this time? I just made it lowercase. Is it going to be lowercase? Is it going to be uppercase? Yeah, it's still the original because it printed that out, but we didn't save that. We didn't save the change. If you want to save the change, I'll do it on that other one. My string is reassigned. So my string equals my string dot replace all of the L's with the hashtag. Now we've actually changed what it is. So the behavior is built in, that's what it is. And lecturing on that would be rattling off the list. Every one of those is on the list in your textbook. It's probably right near the top of it. I think it's in order of usefulness in alphabetical order. Some we use a lot more than others. But y'all can read that list. And if you have any questions, let me know. Okay. Close that. The other thing I did want to talk a little bit about, and this will take about 15 minutes. Yeah, so the methods for strings is really just rattling off that list, and y'all can read that list. And I forgot markers, and the smartboard is not nearly big enough for the picture I want to draw, so I'll be back in 10 seconds. My office is straight across the hall. All right, maybe I'm getting used to the smartboard. Already starting to forget markers, but I think I've already forgot markers a few times this semester anyway. Can't really blame the smartboard. So it's been a couple weeks. Not everybody had me in the earlier class, so you may not have seen this. But to describe what's going on inside the machine, I use a picture that looks like this. It's called a stack heap diagram. And those names, stacks and heaps, those are types of the things we're getting ready to talk about. Those are more advanced types, so we won't quite get to it. A stack is, well, somebody said, a stack is like a stack of plates. That's how computers actually run our instructions. When you wash dishes, right, finish eating your meal, go wash dishes, the last plate to get washed is the first one, is the top of the stack. So the last plate to go on that stack is the first one to get pulled off the stack. That's how computers run our instructions. We write the codes going in order. Then in Python, the computer reads it in backwards so that the very bottom line gets read in first, and then line 1 is at the top, and then it starts pulling them off from that. A heap is a much more complicated structure. Optimal efficiency, this is as good as we can set up for, this is as good as we can make a machine go in a heap. So they'll show up in much later classes. You might see it in a 200 level class talking about data structures time if there's extra time, but that might not see that specifically till a data structures class. And even in classes like the first level data structures, which would be a 300 level class on a 4-year degree, might not get the heaps. They're a little more complicated, but what this picture represents is the stack is our code and the heap is what's actually happening in RAM. So I'll use these two pictures to represent things. First off, a definition, because we're going to use this word a lot. There's a word we're going to use here. Definition. And I'm pretty sure this black marker is going to go out. So I'm going to try to color code things. That way it all fits on one. I don't think the color coding will work. I'll switch markers when it goes out. That's probably going to end up a mess. Let's see. An array is a collection of similar type data. I didn't go off the camera, did I? No. Similar type data stored via a recursive algorithm. So I kind of highlighted the word. Do you see anything there that really popped off that definition related to Python? Yeah, type. Have we ever worried about what we were putting in a variable? We have some data, we put it there, and we don't worry about it, we print it. And then it's what's already there. So because of that, we do not have arrays in Python. But that being said, one we actually have is called a list. I'm drawing a picture of an array and then talk about list. List shows up all the time in our daily lives. A to-do list, a grocery list. Lots and lots of things where list shows up. But the way we use it in our daily lives is not what is meant by a computer data structure list. So what we're looking at here is starting at the data structures. The short version of that, since you won't need to know the actual definition yet, a database is storage and a data structure is memory. We need to get the stuff from storage into memory, around memory, so process it as quickly and as efficiently and as good as we can, and then back out of memory. So our data structure is what brings our data into memory, around memory, and then back out. So instead of using one variable at a time, it's nice to work with a collection. And I have an analogy. Take out the really expensive stuff here. There we go. So, like, okay, time to hit the class. I know a bunch of y'all are a Zoom call, but I think you can relate to this. And we need certain things to head to the class, right? There's a folder, we're gonna need that in class. Look at that. Got a textbook, gonna need that in a school day. Probably gonna need a calculator. Pretty much every time we go to school, we end up having to do some math or another. Might need something to write with. Got a pencil and a pen, might need those. What else I got here? Whoops. Well, I already lost everything. Let me pick all that back up. Okay, and now that I did the lot, got some other stuff. Might need a dry erase marker. What else do I got in here today? Oh, got some aspirin. We might need some aspirin. Okay. Pretending in class for a long day. I need that. So we got all this stuff and I can carry that around. I can get to class, sit down, pull out the parts I need. I don't have a notebook. I left my notebook at home today, so paper to take notes on. Sit down at the desk, pull it out, but there's a better way to do this, right? It's a much better way. I already dropped all this stuff once. Instead of that, I can put all this stuff here. Everybody knows what this is, right? And then I can carry it all. My hands are completely free. No problem. When we get to class, we just look for the stuff we need. And what do we do when we look for the stuff we need? We're intelligent, so we don't think about the process, but let's break through it, break it down. We go to the backpack. It's like, okay, need a textbook for this class. So we go to those items. Is this a textbook? No. Is this a textbook? No. Is this a textbook? Yeah, that'll work. So that's the thing we need. All right, also need a pen. So we go back here. Is this a pen? We start back at the beginning of the collection. Is this a pen? Nope, not a pen. Is this a pen? No, not a pen. Is this a pen? Nope. If this is a pen, I will use it. Well, that looks like a pen, so need that. So that's what we do for a trip to school, right? We can do the same thing with our data. That's what a collection is. And that stack is like a whole bunch of variables, right? All of our stuff is separate. The only thing keeping it organized together is the fact that we're holding it there. That we put it there and know that we know it goes there. So that's like a whole bunch of just random variables. So instead of using a variable, we can just stick it all in a backpack and get carried around a lot better. And then anytime we need something, we just look through and do a simple selection structure to see if that's the thing we want. So you're familiar with the process of why we use collections. And you shouldn't have to think too hard to realize that we'll run out of variable names very, very quickly. Right? What if you're writing a program for a company that has 9 employees? You're going to call them employee 1, employee 2, employee 3, employee 4. You're going to run names pretty quickly, right? Or we can make an employee collection and just check for each particular one there. So starting with arrays, which we often say array, and I will say array in this class, even though we already know it. Do not have arrays in Python. We use something else, but it's like a catch-all term. When we tell somebody, when somebody needs to go look something up, we tell them to Google it. Even if we know they're going to use Bing, we still say Google it, and then they can go to Bing on their own. Or what's the other one? Avast secure search. Even if we know they're going to use that, we're still going to tell them to Google it, even if they're not using Google. Or TiVo, which is a little bit fading out, replaced by Roku. Even though Roku is definitely not the only smart TV, right? There are a lot of smart TVs out there, but we're still going to call them Rokus if we're just generically talking about one, or if we can't actually see the label right in front of us. Or sometimes even if we can see the label, because we know it's a smart TV and we know what the general term used for smart TVs is. I think I said it wrong, didn't I? Is it Roku or Roku? Roku, yeah. So thank you. Okay. It sounded wrong for a second, but y'all know what I'm talking about. Those words that, even though that's the name brand, we use it in language enough that that's what the one we use in language. So what it is, similar data stored with a recursive algorithm. So what we're going to say, let's make up an algorithm. So like next is our start the starting point where we started storing that, plus 3 times our size plus 7. Just making up a math formula there. So 3 times our size plus 7 will get us back to the next one. It's recursive. So this is x1. And then x2 is where x1 starts, plus 3 times the size of our data. Let's say 1 byte to make it easy. Our data is 1 byte, 8 bits, plus 7. So when we say we have an array, tell the computer, all right, we have an array, go ahead and create that for us. It's going to set up the space, and it's going to pick some starting value. And we talked about this with variable names. Maybe if the computer decides to put that at bit number 23,417 in RAM. We'll never remember that. 23 megabits in RAM, that's barely into our RAM in the modern world. Right? Most of us have at least 4 gig. If you only have 4 gig in your computer, you probably already started thinking about upgrading. Right? So we're 23 megabits in. It starts here. 1, 2, 3, 4, 5, 6, 7, 8. There's our 8 bits making up that data. So we know where this one is. And so that's at 23,417 plus 3 times 8 bits for the size plus 7. 24 plus 7 would be 31. And 31 plus 17 should be 48. That sound right to everybody? 3 times 8 is 24. 7 more bring us up to 31. 31, 17 gives us 48. And then the rest of those numbers are just going to come along. So the next one starts at 23,448. So somewhere else in RAM. 1, 2, 3, 4, 5, 6, 7, 8. Oops, that should have just been 7. 7 little divisions make 8 slots per bits to go. And we know that this starts at bit 23,448. And we could keep going, plug in more stuff than that. The computer would keep track of all that, right? That's an exaggerated example of recursive algorithm. Back in the days of heating coils and vacuum tubes and heating coils, we would definitely wanted our stuff spread out as much as possible because we actually turned on heating coils and had to turn on the radiator to cool them down like the early computers when this definition came about. So you would not want to turn on a bunch of heating coils too close to each other. That would just start a fire, right? If you turn on 64 heating coils right next to each other. But they're basically like toasters or space heaters. What would happen if you turned on 64 space heaters right next to each other? You run out the door and call the fire department. So it was very important to spread it out. But now in the days of silicon, our algorithm is just +1. If it's 8-bit data, it's plus 8 bits to get to the next one because silicon is not going to catch on fire. But that's what a recursive algorithm is. And it has to know in advance. It has to set all that stuff up in advance. So the array also has to know if we want to put 10 things in that array or 50 things in that array or whatever. It all has to be set up ahead of time. So it's non-dynamic. We can't change it. If we build an array with 10 things, and then later in our program discovered we actually needed 11 things there, our only option is to delete that array and make it a bigger one with the more thing. Well, copy everything over, then delete the original and go with the bigger one. So it's non-dynamic, static. There's always a trade-off though, right? That's gonna be a lot faster because the computer knows what it is before we ever even start using it. the computer has already reserved those spots in RAM before we even hit run on our program. Or that's the very first thing that happens when we hit run. So before the little window even pops up that we can tell it's running, we already have RAM reserved. The computer knows exactly what's going to be. There is never any time wasted on it. So it's a lot faster. Which computers are pretty fast, but keep in mind things like, I like to use Humana here around Global as a good example. Humana has over 50,000 employees and over 10 million customers. Okay. If you save a millisecond on 50,000 employees and 10 million customers come the first of the month when the bills go out, how much time is that? Like 1 millisecond comes in the calculator. We're going to put the calculator. 1 millisecond is 0.00001 seconds times 50,000 employees, it's somewhere around there, times 10 million customers. And 1, 2, 3, 4, 5, 6. And we just say 50 million seconds. That's a lot of time. That time does add up. So the faster, we don't think about it on our, because at small scale, it's not a big deal. But writing software like that, it's also going to pay a whole lot more, right? So that's the sort of software we have to be writing. And saving 1 millisecond on each item in the array would add up to millions of seconds in the case of a company the size of Humana. And Humana is nowhere near the biggest company around, right? So it is still important to worry about that. We don't think about it on a small scale, but remember, try to approach it from the business perspective. If it helps everybody comes to college to get a job and make good money, businesses are the ones that have money. So we need to think about their perspective. And what we learn from that large perspective will flow down to our personal usage file. We always think about our personal usage. It's hard to scale that up. But that's an array. We don't have those in Python. So let's move on to the next one. Yeah, the next one is the one the picture is going to show up of, and then two more definitions. Or actually, I'll just list them out. Oh, I forgot to ask you. Okay, if I erase this, it's been up here for a minute. A list like markers. That marker worked great 5 minutes ago. Oh, it's not going to be big enough, so I'm going to draw 3 of these pictures.
To the new screen?
It's not going to be big enough for the pictures. I've been trying to use it, but I'm going to draw 3 of these. And I want them side by side, so we have to flip to other screens to see them. So a list, this is the one we actually use in Python. A list is a data collection with pointers with a pointer to the next element and no pointer terminated. This is the one we actually have in Python. Well, maybe I will just draw one of the pictures. It's okay if I erase the right picture in here. So remember that the computer sets it up ahead of time, knows exactly what it's going to be, nothing else, no matter how many pieces of software are running on that machine, those are our bits in RAM. So that makes it a lot faster. It's a lot faster. So for a list, we tell somewhere in our code, we say we want a list, and it points at the first one. And then instead of that fancy math formula, we have a pointer to the next element. So we add just a little bit of data on the end that points up here. Says there's the next one. We add a little bit of data on the end that points up here. And then at the end, it's null pointer terminated, null terminated. Usually we leave the pointer off. So at the end, we just have a pointer going to nowhere. It's electricity, so at the end, there's extra, the electricity wants to flow somewhere. So at the end, this electricity just flows back to ground. But our last pointer points at nothing. The electricity, we don't send the electricity anywhere. It's like, okay, we're done with that electricity. We need to do the list. It's very dynamic. So if we need a bigger list, what can we do? The list exists because we're just pointing at the next thing. So we just come here to the end and say, okay, oh, we got something else. Let's put it in here. And then it's the one that points at nothing. We've got another thing in our list. If we want to get rid of this one, all we have to do is stop pointing at it. Like, oh, done with that one. So I'm going to make another piece of data up here. Break this pointer somewhere along the way. And then the first pointer points up here. And then afterwards, this one points down here. So now nothing points at this one anymore. It's not in our list. So a very simple thing, it's dynamic. A lot more overhead comes with it, obviously, because you have to constantly make those adjustments. But this is what we actually have in Python, a list. And we'll just say array over and over and over again. But does that picture make sense? We just add a little bit of that on the end that points at the next thing. And with arrays and lists, we index them with integers. A list, we're going to index that with an integer. So everything just automatically gets an integer. So at first, this one was 0, 1, 2, 3. And then when we stopped pointing at this one and pointed over here instead, this became index number 1. So we refer to it by an integer. That can be useful, but sometimes there might be something better than an integer to refer to that, right? We have to actually keep track of what we put in index 0, index 1, index 2, index 3. Or other times, we don't care about the index at all. We want the whole collection every time. Doesn't matter how many are there, whether we don't care how many are there. We're going to go through that whole collection every single time. So we don't need the indexes at all. So the next one is, well, I'll just put the list up here. That's the only formal definition we need to get to. So the next two I'm going to just write up here. So a set is a collection with no indexes. I'm not going to get into how it's stored internally. Collection with no indexes. So if we put 10 things in there, we have no way to refer to only the third one. All we can do is we can look at all of them or none of them. Obviously, that's going to be a lot quicker because we don't have overhead keeping track of which one's which. We don't have these extra connections to keep the order. Sets might not come in the same order every time. It's going to come in whatever the computer decides is the most efficient order to get it to us. Time efficient. So it's going to come in whatever the computer decides for the moment will be the quickest way to get us that data. It might be completely reversed from the way it gave to us last time. The order will change. In a classroom example, it's going to be small sets, so it's probably going to come the same way every time. And then the other one we're going to look at is a dictionary, which is like a collection or a list. As far as using it, you're going to think of it as list because you're going to use these two most often. This is what we call an array in Python when we're just generically speaking to other programmers. A dictionary is a collection indexed by strings. A hash table would be more advanced. If it uses a hash table, we create a set and a hash table. Since he asked, I'm gonna draw the picture. I was gonna leave the picture off, but somebody asked. So a set or all that, keep the same data points. So if we wanted a set, we have an initial pointer to each one. So instead of extra data, we basically keep our pointers right there. And to turn a set into a map, which dictionary is one type of map, we can use anything. It's just very rare that we have a reason to use something other than integers or strings as indexes. Because those are the useful ones, right? It just makes the most sense to give it a number or give it a word. But it's actually a map. What we do is we create a hash table. Hashtag is named after a hash table. Hash jump table is where that word comes from. And instead of all of these pointers, I'll just write dictionary because we're not going to talk about the full maps yet. Instead of all of these pointers, all of our data points at a spot on the hash table. So instead of pointing at other data, it points to the hash table reference to itself. And then somewhere separate in RAM will store a bunch of strings and line those up on the other side of the hash table. So it's a set combined with a hash table. Hash table is really, really hard to explain at this level because that is what the computer does. That is, you'll hear it talked about and see some pictures and stuff, but really that's electrical engineering. That's the linear algebra of tensors, which are matrices composed of matrices instead of individual numbers, nested very, very deep as electricity. And that's what a hash table is. So it's what the computer actually does to make it fast. But that's how a dictionary works. And I wasn't going to draw that picture because it uses words that are hard to talk about in an introduction class, but somebody asks, so I thought I'd answer. Always feel free to ask questions. If you want to go off on a side tangent, I will put that down the rabbit hole for a while. I'm pretty laid back. If we forget to cover something and need a little extra time, I'm pretty lenient about that. Which reminds me, I forgot the big announcement. Did y'all see the announcement come out this morning? The reminder? I'm a strong believer that having everything due on the same schedule is not good practice for the real world. That's why some assignments close, some assignments are open for the whole semester, some assignments have a restricted late policy, and some assignments have no late submissions whatsoever. And some of them are on a different schedule. We only have 2 schedules this semester. Sometimes there's 3. But our exams are on a different schedule than the homework. So make sure you're aware the exam is due on Saturday. There's 2 parts. One part's a bunch of multiple choice questions. And I think I'm behind on doing so, but like the quizzes, I'll go back through and double check that because computers aren't really very good at grading stuff. Computers can only do an exact match, right? If you fill in if it says, match, M-A-T-C-H with a capital M. The only thing a computer can grade if that's the answer is if what the person typed is exactly equal to M-A-T-C-H with a capital M. That's all a computer can do. They're not very good at grading, so I always double check those. a lot of times questions are vague, so if I can see how you got one of the other answers, even on my multiple choice, I'm like, oh, I see what you were thinking there. So I do look back over those. And the programming, there's a programming part, which should be a whole lot easier than your homework assignments. But the exam is on a different schedule, and it closes on Saturday at midnight. No late submissions, unless you're in the hospital right now. If you're lying in a hospital bed, probably barely conscious, at 6:45 on Wednesday night, obviously there's an extension. I know he's gonna watch this. Whenever he wakes back up with emails and stuff. Obvious extension there, but I'm already aware of which people in the class are laying in a hospital bed right now. So make sure you get it to me by Saturday. Or let me know, get a hold of me. Won't be always get a hold of me if something happens, but the policy is no late submissions. And I try to hold real tight to that on the exams. So keep an eye on that one. So that was the notes on the board. So we just need to see the basic syntax, but the basic syntax of these is in the book as well. And then we'll get on to that important part that's not covered in the book. So arrays, I believe most of y'all would have solved in the SDEV 120 class, right? We want to create an array. We'll say my array equals, and use square brackets, and then put a comma separated list inside of it. Well, it's actually a list, it's not an array. So maybe I should call it that. Instead of my array, let's call it my list. And then we put some data in there. 1, 17, 23, hello world, true, false, 0, 0, 1, 0, 0, 1. We haven't talked about any colors. I'll just write it as a string blue. We haven't talked about any sort of color thing. We can color stuff in the console. I'll look at that later when we look at the emojis. And not the colon parenthesis type emojis. We have the full, there's a lot there. It's been a while since I scrolled all the way to the bottom of the emoji list on my phone, but we can put those in the console. We have those, obviously. Python can output our stuff that computers can output, so we can output emojis. We'll look at that soon, but we can put an emoji there too. And then we can do a few things with that. Oops. I want to erase that line. So again, that shortcut, I'm going to click anywhere in that line. I'll just hit the middle, then push in and hold shift and home to quickly clear that whole line out. And that should work in every text editor because shift is what we did before the mouse was around. So that goes all the way back to the 50s with the keyboards. The 40s when we put a keyboard on a computer. Then we can ask for the whole list. So like print my list, or we can index it one at a time, print my list. And lists are indexed by integers. So index number 3, which one more thing, I guess I could have talked about it when I was had the array picture up there. It would have been the clearest to look at. I kept drawing these data these things here. Right? Here's all the bits making up our data point. When we ask for it, we have to ask for that, where that first bit starts, right? So we ask for this. So it's where that data is plus nothing, plus 0. So start plus, oops. Start plus 0. But we don't count that if we only read 3 of those 8 bits that we have our data. That's not enough, right? if our data is stored as an 8-bit integer, we need all 8 bits. So we don't count it till we get to the end. So we count at the end. But what comes right afterwards? Our next start point. So we don't count it until we get to the start point from the next one. So that's where there's that discrepancy. We index from that ask point. Start plus 0. We know it's 8-bit data. So start plus 1 is 8 bits over to the next one. Or 8 bits over, it's already erased, but 8 bits over, there's a pointer. The computer hits a pointer and goes to the next one. So that's where those indexing numbers come from. Ask for the beginning, count at the end, and we always have that discrepancy you'll need to keep track of. And it changes language to language. Some languages start at 0, just go right with that. Some start at 1 because it's more intuitive. And some start at 1 because they put something in index 0. We can't use index 0, language does. SQL uses index 0. So we have to start at index 1 in SQL. So if Python starts at index 0, so if we're intermingling Python and SQL code to work with an actual relational database, we have to make that adjustment between the indexing because it'll be off by 1. Sometimes it's because starting at 1 is more intuitive for humans, and like in the case of SQL, other times it's because index 0 is being used. The language itself is using that. Then we have for loops, right? So for item in my list, print item. I don't think there's any surprises there, right? I should save this. Let me pull this out of the way so you can see the code. Documents, delete. This is collections. So no real surprises there, right? We get the whole list. The second time we said the third. Index 3, so the 4th element. It goes over to the 4th element, which has to be that word. Then we loop through and printed them out one at a time. Or we have that range function for index in range length of my list. And then in our for loop, print my list, whatever index we're currently on. All of that should look familiar. Right, so nothing new there. A set, a lot of times we do this. Okay. You've probably seen me do that a couple times Monday night. I remember doing that a couple times Monday night when I did the collection. And the only times I did it this way is if I was looking for a particular one. So a lot of times we need that whole collection and not just one little piece of it. That's where a set actually works better because some of the overhead with the list isn't included in the set. And if we want the whole collection every time, we might as well cut out that overhead and save a couple milliseconds. So like my set is very similar, but we use curly braces. Stuff 23, 39 through, I'll just do it that way. So if I come down here and try to print something from that now, print my set and run it, it's fine. Prints out the whole set, shows us everything in our collection. But if I try to print my set index 2, the third thing, we get a problem. Type error, set object is, I should have downloaded Python 3.11. You all have a clear error message on sets. It's still a type error, but they improved the error message. Set is one of the ones that the error message improved on 3.11. That's still running pretty damn error. I think I downloaded it, I just never connected it to Spider. But, it's not subscriptable. With a set, we either get the whole collection or none of it. I'll put that in the comment here. Sets are all or none, which is quite often what we want to do. And then we can just look through it the same way we did the list for item in my set. Print item. And I forgot to do something the first time, so I'll put it here. If stuff in my set print is there. If what did I put in there? Stuff 2339 true if 27 in my set print I guess the same thing. Else print can't find it. Not that I see. Which I should probably copy up here. Else that. So I was typing that code awful quick, but that should look all straightforward, right? There's nothing new there, but it's probably a new combination, right? Y'all have seen if else, you've seen in, but you probably haven't seen in an if else yet. And we found the first one because it is there. It's in the set. But we couldn't find the second one. So nothing new, but a new combination of things. Most likely, some of you all may have encountered that. Right? We're a couple weeks into writing Python code. The other one, which is really, really useful, is it's an extension on set. So my dictionary, we're going to use curly braces, and then we set things up. So I'm going to organize it. So like name, then a colon, and the data we want to store there. I'll put my name. Let's use my data. Age, colon 44, comma, town. Gotta move the Zoom pictures. Oh, I did that wrong. Town, then in the string, then a colon to say we're past the key, and then our value, which is the string Clarksville in this case. So it's a key value pair. So we have instead of indexing it with a number, the number from the order we put it in, which is actually how far it is from where we started storing that data. Because it'll take the size into account. We ask for the beginning, and then we add however many we've already looked at, because once we go over that far, it's a pointer to another item, so it just jumps what the cursor is looking at to the computer's looking at to the next spot. And we can ask for our key as the index instead of a number. So a very, very useful thing. But we have the same stuff. Print my dictionary. That did take a lot longer than I thought it was going to. Print my dictionary. And then the index is that key. We ask for the, so we don't have to ask for the number, we can actually use a word. So a lot more useful. Very, very useful in refactoring, because then we don't have arbitrary numbers in our indices. We have a string that actually says what it is. It's like using a collection and meaningful variable names at the same time. So a lot of people like those. But the other stuff still works too. For item in my dictionary, print item. For item in range length of my dictionary, print. Well, this one's going to be a problem. Okay. Because we use the range function, that gives us a number. So we can't index it that way. So the range, just pay attention to stuff like that. But the other one would work if, actually let's type this both ways. Chris I'll go to the selection structure in my dictionary, print, found it. That sounds good. Else, print not here. And I'm going to come up here somewhere and spread things out. Print. Right. All right, I'll just do 3 empty print statements to spread things out so we can tell where it is in the console. Spread that out. There we go. So when we get down there, it says it's not here. But I was looking right at it on the screen. I know it's there. It should be there. Dot. If I push dot, notice we have a couple of options. Keys, because we have 2 things that it could be, right? It could be the keys or the value. It's not a key. If I run this, it's not there. But what about values? So pay attention to the values or the keys. For reference purposes, I'll comment the one out right above it. If name in my dictionary.keys. That way you have it it's on the GitHub, so you can have the reference. So quick pass of the syntax, very, very quick there. But you all have already seen that before. There should not have been anything new there. Well, yeah, there should not have been anything new there. It's a new combination of things you've seen before. That's why I was so ready to go through it so quickly. Because we've already seen these things, just a new combination of them. And that's where it goes from here. You've seen all the basic tools of programming by now. We have more refined version. Next week is just improvements that are on top of basic programming. GUIs and objects, we can't use those in everything. If we're embedding code in a engine, we probably don't need a bunch of data objects to hold strings and stuff for the code that runs a new Mustang engine. We have a different need. But you've seen those basic pieces now. There's just different combinations of how we can put those together. Basically, that's where the rest of the software development program is. And then afterwards, experience in the field, seeing more and more and more combinations of how those can go together. That's why they often ask for, just, I guess the standard is 5 years experience. That's kind of overdoing it. If they're asking for 5 years experience, they should really be asking for somebody with a PhD because they want some top tier stuff. But probably a year's experience, looking for somebody that's had an internship. You'll see that all the time. Right? You've had at least one job that you weren't fired from. That's like the bare minimum. But everybody's different. But when you see that, it's so that you've had time to see all the different combinations you can put these tools in. Which actually, I shouldn't say all the combinations, because it is definitely an infinite number of combinations we can put these tools in. There's another one I want to throw in right before we take a break. Because got some numbers in my list and some stuff that's not numbers. I want to make a new list, filtered list. And I'm going to quickly type a list comprehension. You are not required to know a list comprehension for this class, but X for X in my list if X dot is Is numeric. I always forget the name of this method. If X is numeric and X is less than 20. I think it says numeric. I might have typed that wrong. IDEs have lied to me about it before because I recognize those words, that word from a different spot than the one I actually want to use. But if it's a number and it's less than 20, then add it to this new list. It's not numeric. Oh, maybe it goes here. It is numeric X. Nope, that's not it. Actually, I think I have to, might have to do this. Is numeric is one of those behaviors I mentioned earlier about strings. We can tell if string is a number. So we have actual numbers. We have to turn it into a string, check if it's a number, and then our condition. That's called a list comprehension. We have several types. We also have generators, yields, several other things still to come. So, but everything in line 18 there should look familiar. Does anybody, you might not have seen is numeric, but we already, earlier tonight, we said strings have methods built in, so any behavior we could need. So obviously you probably already guessed that we might need to see if the string is a number sometimes. So every behavior we need is built into strings. You might not have seen that one, but everything else there should look familiar. Just a new combination of it. And this is the second pass at it, right? Y'all already saw all these tools in SDEV 120. So this is the second pass at all the tools. That's all the tools. But there's an infinite combination of ways we can put those together. That one's called a list comprehension. It's definitely not in the book. I'll leave it in the material here. List comprehension. Oh, I guess I should do a tuple real quick. My tuple is just like a list, but use parentheses, 3, 4, 5, cannot be changed. Has everybody seen a tuple before? So a tuple is non-dynamic. If we need to change that, we have to delete it and create a new one. So to start with, it adds a nice little security measure. We can't accidentally mess up our data because we're not allowed to change it, period. Otherwise, it's just like a list. Cannot be changed. Otherwise, just like a list. I'll just hit run to make sure there's no typos, and we don't really even need to see that. I guess, actually, we could look up here in the Variable Explorer. Variable Explorer, and you can see on, it's a tuple, and it's colored in purple. There on my screen. And a tuple, you cannot change it, but it's just like a list. Index 0, 1, 2 in that case. But for everything except assignment. Okay, that took longer than I thought. Yeah, I've been so far off on taking time, judging times lately. I thought we would be to the next section about 25 minutes. But it's probably a good time for a break. We're right in between stuff. And the next section will take about 45 minutes. That's what it usually takes because we have to actually download some software and wait for the other software to run. Is Joseph here? Okay, yes. As far as I know, Joseph, I think you're the only one with Mac. I wrote down some software, but then I forgot my notebook at home this morning. So I'll have to send you email with the software to use as a Mac. It's equivalent to the Windows software we're going to look at. And I'll just send you the name of the one. I'll send you the name of a couple that I recommend for a Mac later. But the next thing is, what do we do when a program is finished? That's an important thing. So, does 10 minutes sound good to everybody first? Okay. And is anybody else on a Mac? I only know of one Mac user in the class. So if you use a Mac, please put it in the chat room. And we're going to look at a Windows piece of software. So if you use a Mac, you'll need a different piece of software. And I'll send you the name of it later because I forgot to bring it with me today. Otherwise, the clock says 7:11, so we'll get back to it at 7:21. Oh, we're free.